When stars like our Sun die, they form into a white dwarf. They are defined as a low-mass stellar remnant composed of carbon and oxygen that has exhausted all its thermonuclear fuel. The discovery of white dwarfs was first sparked in 1844 when a German astronomer studied the brightest star in the sky, Sirius, and found that a smaller star was orbiting around it. In 1862, the white dwarf was discovered with a telescope and was almost missed as it was hard to spot in the glare of Sirius. In around 1930, another astronomer theorized that if the nuclear power generation of the center of the star is exhausted, it will gravitationally collapse until it is supported only by the force of particles against each other, which explains how white dwarfs are developed. Data shows that stars with initial masses of 0.08 to 8 to 10 solar masses will become white dwarfs when they die. When stars become white dwarfs, they are about the size of Earth and no larger than 1.4 solar masses, because at that point they become unstable. A star begins to die when it can no longer go through hydrogen fusion. This leads to the red giant phase, where it fuses helium to carbon and oxygen. When it goes through the red giant phase, the star expands and sheds its outer layers into a planetary nebula. What's left is the white dwarf, or core, of the star. Over time, it will cool off and grow dimmer until black.
Neutron stars are just a ball of neutrons after a massive supernova. They can only be formed from stars 8 times the mass of the Sun to about 25 times. Now, due to the star collapsing so fast, protons and electrons are forced to combine, making neutrons and neutrinos. The neutrons fall to the center, which form the very compact star. Degeneracy pressure of neutrons is what supports the star against gravity. Neutron stars are very small compared to other stars. They are about 6 miles across, which is the same size as a small city. The star has 10 to the 51 neutrons in it that are chargeless. Now the mass and weight of the neutron star is what sets it apart in my mind. Just a single teaspoon of the star would weigh the same as Mount Everest. Imagine what the weight of the whole star would be. In 1967, Jacqueline Bell, who was at the time studying in Cambridge, England, saw very regular pulses coming from a specific part of space. The first original thought that was made about the pulses was LGM, or Little Green Men. They thought someone, or something, was trying to contact us, although we now know that the pulse is actually just a pulsar. A pulsar is just a spinning neutron star. Now, what exactly is a pulsar? A pulsar is a neutron star that sends off radiation. If you think of a lighthouse, it may help. You get glimpses of the light every time it rotates around. If you look at the picture, you can see how the axis of the star is straight up and down, but the radio emission from the neutron star isn't exactly on that axis. So, as the star rotates, so do the rays of the emission. We end up missing and not being able to see a lot of neutron stars because Earth is not directly in the path of all those beams. The radiation that the star puts off is electromagnetic and created by electrons. These stars are able to spin so fast that they can be up to 1,000 times a second. There's actually a pulsar at the center of the Crab Nebula supernova remnants that pulses 30 times a second. That's every 0.033 seconds. The strong magnetic field coming from the neutron star is what really sends out the radiation. With the star pulsing so fast, it just shows how small the star has to be. The star gets this small from collapsing of neutrons. With it being so dense and small, it really shows off the conservation of angular momentum. The surface rotation velocity is about 60,000 kilometers per second. That is such an enormous velocity that if it were anything else spinning that fast, it would be torn to pieces. A binary system is when two stars end up orbiting each other. In these situations involving neutron stars, matter falls from another object and starts to form a disk. This disk is called an accretion disk. It adds to the momentum of the neutron star and makes it spin faster. The matter that falls toward the neutron star may become very hot. When matter falls onto the star, you get a burst of X-ray radiation for only about 1 second. When that happens, it makes the system an X-ray binary system. Quantum mechanics states that neutrons cannot be in the same place and be the same state at the same time. So, what that means is a neutron star can only condense so small. The neutron degeneracy pressure can no longer support a neutron star if its mass exceeds 3 times the mass of the Sun. The neutron star limit is set and no force, even degeneracy pressure, can resist the gravity in that point. If it occurs, then it crushes all the matter into one point, known as singularity. And to recap, a neutron star is a ball of neutrons left over from a supernova and is supported by neutron degeneracy pressure. They were discovered from beams of radiation that cross space to get to us, which appear as pulses, or also known as pulsars. In a close binary system, accretion disks form, which can be hot enough to produce X-ray bursts. Quantum mechanics states how neutrons in the same place cannot be the same state. However, the degeneracy pressure has a limit of 3 times the mass of the Sun. Beyond the neutron star limit, there is no force that can resist the crushing force of its gravity. It brings it all down into a single point called singularity.
Black holes are the result of a star collapsing to a fraction of its previous size. When it collapses, all of its mass is concentrated into such a small radius that its density warps space-time around it. The gravity is so strong that anything that enters the black hole will never escape. The escape velocity is that of the speed of light, which is called the Schwarzschild radius. And according to Einstein's theory of general relativity, nothing can exceed the speed of light, so essentially it's impossible to escape. Not even light itself can, which is why it appears black. The surface we see when looking at a black hole is the event horizon, although it is not a surface, it is just a boundary in space. The smaller stars form stellar black holes, which have a much shorter event horizon, so objects that enter this will be stretched out very quickly. Because each measurement, the gravity gets so much stronger that the force acting upon the bottom of the object could be millions of times stronger than that at the top. Stars, for example, release a huge amount of energy when being destroyed by this. With supermassive black holes, the event horizon is much longer, like in the picture, so it would take a lot longer to get to the stage of being completely destroyed. If mass is added to a black hole, it will increase the event horizon. When approaching the event horizon, time is increasingly slowed down. So if you were to enter a black hole, time would seem to go on normal for you, but if someone from far away was observing, then you would almost seem to freeze in time because you would be going so much slower than them, until eventually the light from your body that emits would no longer be able to escape the black hole and you would just turn redshift and disappear. From your perspective, right before you're stretched out to your death, you would see the whole universe and fast forward and see all there was in an instant. The point at which nothing can resist gravity is known as singularity, and this is what a black hole reaches. It is still unknown what lies at the singularity, but if you were to find out, there would be no way to tell anyone else. The gravity, however, is only effective if something is very close to it. So using this, if you were to replace our sun with a black hole, the Earth would remain essentially in the same orbit, but Earth would eventually die due to no heat or light. Another clearing something up is black holes don't suck, which some people think they do. To show this, Einstein came up with the idea of space as like a fabric stretched out. If you were to put an object on the fabric, it would go down at a certain amount depending on the mass of that object. This can show you how gravity warps space-time. As you can see from this first picture, although a star may appear to be in a certain spot in the sky, due to the certain factors like the sun's gravity, its shifts are our perceived location and the star really lies at a different spot. Black holes are the ultimate case of this, and they are at singularity, so it warps its perspective of its surroundings the most, as it would create the biggest drop in the fabric. And who knows, maybe one day this could lead to passage of space-time and wormholes.